Okay, looking at torque wrenches and the proper procedures for using the torque wrenches to be able to get and break torques and to get to the specific torque that manufacturers require fasteners to be torqued to. So I'm going to introduce a bunch of different tools for your usage. So first of all, the torque up to a torque rating, we need to look at the procedure on how we're going to do that, but I want to introduce a couple tools, first of all, for breaking torques, because there is a misconception that a torque wrench can be used to break a torque. Sometimes they may be used to check the torque on a detorque sequence to find out if those fasteners were at their torque value. And sometimes that torque wrench is used on a tight fastener to calibrate to see exactly how far out it is in comparison to another one. I would highly recommend that anytime you are doing a detorquing sequence on an engine or any other related components, that you use the appropriate tool to break that torque. And I've got a couple different ones here. One, for example, is an over-length 3/8 drive flex head socket, or pardon me, ratchet. This gives us the overall length that we need to increase the torque so that it's not as hard doing it. If we were using a really short one, then we're changing the fulcrum point and it's going to be a lot harder for us to break that torque. Plus, that means we physically have to use more force and we put ourselves at risk because of an incorrect tool and an incorrect procedure for detorquing. So the longer the longer the tool is, the better it's going to be and the easier it's going to be for the technician to actually break that torque. So this is a 3/8 drive, for example, and the next one I'm going to take a look at here, it's a little bit shorter, but again, depending on the torque that you're working with, if you're only detorquing, 100 foot-pounds, it's not going to be that hard for you to break with a little bit of a longer wrench. So this one here has a flex head on it. It has a ratchet drive that can be flipped either forward or backwards to lock it into position. And then you can put it in the appropriate position where you need to get into or use it to break that torque. The other thing that a lot of technicians forget about when they're breaking a torque is the position and the stance of your body. And really, we need to have one foot back so that when we're breaking a torque, if we slip, we're constantly in control of our body so that we're not creating kinetic energy from the detorque sequence to putting that into our body, which then, if we're not standing correctly, can throw us off balance and potentially cause us to wipe out in the shop and run into something and maybe hurt ourselves. So again, posture is a very important thing when torquing or detorquing any fasteners that we're related to in the trade. So this is another one. This is a 1/2-inch drive flex head, very similar to the 3/8 drive one that I talked about. And this one here, being a little bit larger, has a positive lock on the ratchet head so that it holds the socket. So now when you're torquing or detorquing, and this is not a torque wrench, but when we're detorquing, then we don't slip because the the socket comes off the end of the drive. So again, the positive lock is to keep that socket in place so we don't lose it, because sometimes we might be torquing or detorquing upside down and we don't want the fastener falling, or the socket falling off of the fastener head. So using larger tools allows us to use our body more effectively to create that detorque sequence. So next one I'm going to take a look at too, and this one's a little bit larger. This was a 3/4 drive. We looked at a 3/8 drive, a 1/2-inch drive. This one here now is a 3/4 drive. And of course it can go forward or backwards. It's fairly short, so if you need to get into a particular spot, and again, torquing or detorquing, again, we don't want to push, but if we're detorquing in this particular fashion, then we use a larger wrench that takes less effort on our body. This one here also has the availability to increase its length. So when we increase the length, then of course, it takes less effort for us to pull and detorque that particular fastener. And again, it goes even longer so that we have a really long tool to, again, take less effort on our body to take that torque out. So that's just the gist of looking at a few tools for creating a D-torque on fasteners. The next one we want to take a look at is the torque wrenches themselves. And I have a bunch of variations and a bunch of different styles and types that are used. This one here in particular is a deflection style gauge. Is not normally used in the trade. We typically see a click stop style, and I'm going to introduce that one also. But this one being a deflection style gauge allows the fastener under torque to bend this bar and create the correct torque. So I've got a fastener set up in the bench here, and I'm going to go with this one in particular, and I'll talk about this here in a moment. This one is a inch-pound torque wrench. And when I have it on the fastener, if I'm going to use it, and pull it up to torque, for example, if it's a 10 foot-pounds on a inch-pound torque wrench, what we're doing is we're dividing it by 12. So, for example, if we had 144 inch-pounds, that would be 12 foot-pounds of torque. So whenever we talk about the inch-pounds, then we have to divide it into the value to get it based on 12 inches in a foot. So this one here in particular, I'm going to just swing this, and it's not a lot of torque, but again, posture on my body, and I'm going to pull this up to around 144. Now, the gauge moves on its own, but we just have to take a look and follow where the gauge deflects to actually see the value. So after doing the torquing procedure, then we know that it's torqued to that particular value. So that's the one style of gauge that can be used. The next one that can be used is a click stop. And again, it's got the ratchet head on it, can go forward or back. And we use the dial scale on here to dial this up to, and I'm just going to run this one up to about, we'll stick with the original one that we talked about at 144. And we are at I'm going to go to 150 on the scale and then back it down to 144. So then we lock this so that the value cannot change during the procedure. And then again, we just pull on it until it click stops. So that's the style that is used for click stop torque method. So all we need to do is see that this wrench changes. Now, one of the things that I find that technicians tend to do is they may under or backhand this and pull it so hard that they're pulling into the click stop and then further on the fastener. If we do that, we've gone beyond the torque. One, we can potentially damage the internals of the torque wrench, throwing the calibration out. And two, over-torquing the fastener beyond its tensile strength, which can cause failure within the fastener. So it's really important for us to make sure that we're not over-torquing. And you can see I'm just using a few fingers on this for a bit of finesse because I want to feel the torque wrench do its job. A common thing that I find also technicians do when they're torquing something is that they do a double click. And that's fine because one, we pull it to it, and two, we check it. And that's okay. Just don't pull further on the second click. So here I can just click this thing all day long and it's not going to go any further than the torque rated value that I have on the wrench. So that's looking at the torque wrench with the click stop apparatus on it, or a dial indicator on it, and the click stop apparatus that we use within that gauge. So looking at the next tool here, and this is a very small one, and again, depending on manufacturer, depending on where you have to do the torquing, we use the appropriate style or size of ratchet with the torque wrench. So this one happens to be, it's a very small one. Normally it would be a 1/4 inch drive, but this one happens to be a 3/8 drive. And I have this one dialed already at 144 inch-pounds, which would be the corresponding foot-pounds. And again, we put this onto our fastener, and with little effort, I can pull that to the 144 inch-pounds or the 12 foot-pounds. Okay, and you can hear that one physically. So the next one we want to take a look at here is the 3/8 drive click stop inch-pound wrench. So now moving up into different size and different types. Again, this is another one. It has a lock on the top here. We have the dial indicator on it for dialing in the value. And this one here, I'm just going to put a little bit of a larger torque on this right now so we can physically hear it. And I'm going to go with about 60 foot-pounds. Okay, so when we go with 60 foot-pounds, and the fastener that I'm using in here, we're not going to talk too much about fasteners, but I'm using a grade 8 fastener locked down on the bolt in the vise so that I can just do a demonstration on this. Fasteners are a whole world of their own, understanding the values, the length, the size, the application, the thread pitch, the thread type, fine thread, coarse thread, the class fit of the fastener. All these things can be referenced into our textbooks or literature that's found on the internet. It's a science on its own, and the type of fastener always depicts the type of torque that the manufacturer through engineering determines has the right amount of clamping force and the right amount of distance that it's pulling a component down to hold it into position. So this one here, this is a grade 8 fastener that I have on here. The grade 8 fastener is somewhere around, it's about 120 to 130,000 pounds of shear force on that. And we want to bring it within a certain tensile strength. And it's usually, when we do a torquing procedure on a fastener, we usually take about, it takes about 80% friction load to wind that fastener onto its threads and against the friction on the underside of the bolster of the head of the bolt onto the washer or onto the component to actually create that torque. We have on average, and different literature supports this, anywhere from about 10 to 20%, so maybe 80 to 90% friction to actually attain the torque, and anywhere from 10 to 20%, looking at different values, on how much it takes to actually maintain that clamping force. And different manufacturers, based on the clamping force effect of all the fasteners across the entire component that's being torqued, will create a certain amount of clamping force to hold that fastener in place. And some of them, like for an example, a 60 series Detroit engine in a diesel application, all the fasteners that are torqued to the spec that they recommend provides over 1 million pounds of clamping force between the deck and the deck of the head and the deck of the block and the gasket and the liners in position. So they require that because of the pressure and the force that's on those components during operation. So going back to this torque wrench, I now have it set at 60 pounds. I put the lock on it. It's locked. Again, putting my body in the correct position for posture and pulling on it. And I may have abused this fastener where it's actually, no, it's going to torque. So you can hear that one pulling up to that torque of 60 foot-pounds. Now, on the video, I've had to pull this a couple times. Normally when we're doing a torquing procedure, we want to try and do it in one sweeping motion. So I had to pull on this about 3 times, but normally we want to try and get it run down and then pull to that torque. So pull up to it and not beyond it. And again, even if you backhand this, I'm only going to go to that click stop that we can hear as an audible tone. The technician, once you have this in your hand also, you can feel when it comes to that particular torque, and you can hear it audibly, and you can also feel it tactile-wise with your hands. So that's torquing with the 1/2-inch dial style or click stop style of torque wrench. So next one I'm going to take a look at here is a flex head digital torque wrench. Now the digital torque wrench, it has some good attributes to it. It does not have a locking head on this style. The cheaper brands tend to have a locking head, and the Snap-on one does not have a locking head. And this one here, I'm just going to cycle through and I will show you what the screen looks like momentarily. And it goes in different increment values, Newton meters, foot-pounds, and I'm in the foot-pounds range, and right now it's showing them up around 150 because that's where it was left last. And I'm going to put this one around 30 foot-pounds. And we'll just see where we get to. Of course, we already know the fastener's torqued to 60, but again, I'm just going to pull on this thing, and you can hear a buzz that happens. In fact, we'll just bring this one up to the 60 that I already have it at, and maybe we'll go just slightly beyond so that I can show you it pulling up to that torque. So I have it set, we torque this with the deflection or the click stop at 60. This one I have set now at 62 foot-pounds. And again, holding my hand on this, again, posture, backhanding it or overhand, and I'm going to pull to that torque. And you see I've gone a little bit further, and it vibrates. Okay, it also makes that audible tone. And this is probably one of my least favorite styles of tools, simply because I think with electronics, there's always the possibility for error. Now, that's just my personal preference. The most accurate would be the deflection style, because this one has to be calibrated. This one, or maybe even the batteries are low, so it's out of calibration because the batteries are low. This one, if you think you're out, all we need to do is reset the deflection meter at 0, and it's good to go every single time. So that's the half-inch drive style torque wrench, and not for any brand recognition, but that one happens to be a Snap-on, and it uses a vibration mode as well as an audible beep that lets you know when you're at that particular torque. The next one that I have here, and this is a little bit of an older Snap-on one, and I have this one set right now at 23 foot-pounds. And just for the purpose, and I know we've already torqued this, but I just need to have something to show some deflection. This one's kind of interesting because it has a bunch of different modes on it. Once I start to pull the torque, the yellow lights come on here. So when the yellow light comes on, it tells us we're under torque and we're getting to the torque. Now I'm slowly pulling on this as I'm speaking here, and once I get to that 23, the green light comes on and says you're right there at that particular point. It shows me on the gauge that I'm actually at the 23 that I have it torqued to. And then if I happen to pull too far, the red and the yellow lights come on to say, caution, you're over torquing, and the red lights indicating you are beyond torque, and it's buzzing. Okay, so it's telling me I'm torquing way too far. So I like this style prior, or in comparison to the last one that we looked at that just has the vibration and the beep. So that one doesn't tend to give me as much finesse as I'm looking for when I'm torquing. And sometimes torquing is not necessarily finesse, but it's the actual procedure to get to the torque is where we need to have the finesse. It's not just always about brute force, because if we brute force this, then sometimes we put ourselves at risk of over-torquing fasteners, and that causes failures, especially on certain applications. So again, if I let the torque off on this, it's telling me that I over-torqued. So now it goes back and recalibrates, and I'm just going to pull it back up to the 23 foot-pounds. And it's telling me now I'm about 16, 17, 18, 19, and there I am at the torque value. And again, it beeps, tells me the light's on, and I can feel a slight vibration when I get to that torque. So the light, the scale, and the vibration to let the operator know, here's where you're at, don't go beyond. And again, for the video, I'm showing you I'm going to go beyond, and the lights indicate an over-torque procedure. Okay, so that's that particular style. So we want to have a little bit of a closer look at the scale on this. So that's the torque wrench that I would prefer if it's a digital application. Now, the other thing that is on here also, and we're going to talk about this when we get into torque angle meters, and I'll explain a little bit of that first as a segue into what we're talking about here. But this one has a degree or a torque angle meter built within it so that the technician does not have to use an additional apparatus that would normally be used for doing torque angle procedures. So this is our torque angle meter, and it's a very simple little apparatus. It's got a scale on it that we can adjust. So we can adjust this to whatever angle we require. When we take a look at fasteners, the fastener itself has the drive or the bolsters on each of the sides of the fastener. These are all in about 60-degree increments. So some manufacturers will actually say that the torque will be set at 100 foot-pounds plus 60 degrees. So then the technician would either have to use the torque angle meter or the degreeing component within that digital torque wrench. So once we set this up, we're just going to put our socket on here, and I'm going to show you this a little bit closer here in a moment. So we set this up so that we're positioned, and then the little anvil, we just put that against something that would normally stop the rotation. So now we can go down and we can set this to 0. So I'm going to dial this now to 0. Now that I have it set at 0, I can use just a regular ratchet, because assuming now that I have this torque to the spec that I referenced was 100 foot-pounds plus 60 degrees. So assuming that I'm at 100 foot-pounds plus 60 degrees, now I can just put on a regular wrench, because you don't need to torque anymore because we're already torqued to that spec, which was 100 foot-pounds. Now, the little anvil on the side stops the scale from rotating as I rotate the ratchet head, and then all I need to do is watch the scale and pull it up to my 60 degrees, which would be 1 flat. So now I'm set at 60 degrees. So now that I see that I'm torqued to that 60 degrees, now I know that the fastener is torqued to 100 foot-pounds plus 60 degrees based on manufacturer specs. Sometimes there'll be a larger fastener that's used on bottom end of engines, on head bolt torques, different things that there is a torquing procedure, a 3-step procedure. So one will be a rundown torque. The second one will be an initial torque, and the third one will be a torque to yield value. When we talk about torque to yield, we're bringing the fastener usually within 5 to 10% of its tensile strength at its maximum torque to maintain clamping force. I mentioned earlier in the video that it takes about anywhere from about 80 to 90% to overcome the friction based on the fastener and torquing it. So that leaves us with anywhere from 10 to 20% for the tensile strength. So if we're in 5 to 10% of the tensile strength, we still have a little bit left for stretch capacity on that fastener based on increased pressure, based on increased temperature, and depending on the component, because we might have a cast block and an aluminum cylinder head, or a cast component that an aluminum component is fastened to, and the manufacturers through engineering decide what that value is going to be and whether it's going to use a generic torque, so 100 foot-pounds, for example, or if it's 100 foot-pounds plus 60 degrees or plus 120. Sometimes they will tell you to use the 100 foot-pounds plus 2 flats. So 2 flats, 60 degrees each flat, would be 120 degrees. So again, we use the deflection gauge to determine where exactly we are. This is a manual gauge that we're using here. So the next one I'm going to introduce here is going back to the snap-on gauge, and just for the sport of it, I'm going to leave this deflection gauge on here and see the accuracy of this tool in real time. Okay, continuing on now, setting this thing at 30 degrees, and I'm going to just dial my indicator back to 0 here, because I'm going to do a comparison between the digital and the manual readout. And I'm going to read this here now on the scale, and it's telling me that I'm at 1, 2, 3, and carrying on through that degrees, and it's starting to go yellow because I'm getting up and close to that 30. Now I'm at close to it, and I'm right on the 30 degrees, and it's showing here that I'm right on the 30 degrees. You can see the green, you can hear it, and if I go further, it'll go red and yellow to again indicate me with a constant buzz. Lots of indicators to the technician that you're over torquing. Okay, so I'm at 34 degrees, and that additional 4 degrees is way too much on this fastener based on the example I'm giving you. So we can take a closer look at that in this video segment. So there's an example of using the torque angle meter on a digital tool, as well as using the manual one that I had connected and did the demonstration on. So both of these work very well, depends on what the torque is. This one here goes up to 300 or 340 degrees and 360 degrees, pardon me, all the way around. That's an awful lot of torque to put on a 1/2-inch drive bolster, so I'm not sure if that would be the best tool for you to use. So going back to looking at the torque wrenches also, there's another style that can be used, and it is a 1/2-inch drive dial indicator deflection style. Again, this one and this style of deflection gauge I think tend to be the most accurate. So when we use this tool in particular, all we do is set it to 0 because we set the calibration every single time. There's no room for error with springs and scales and batteries and digital components. This is all manual stuff. And again, if I set this, and we'll take a look at the scale here in a moment, but if I want to set this at 50 foot-pounds, all I do is pull it to the 50 foot-pounds, and then, as you can see, so when we take a look at that from a closer aspect, you can see that the needle has turned and moved to 50. My deflection gauge is back to 0 again, and I can always readjust it back to 0 so it's calibrated every time. And then the little wiper here, when I pull it to that torque, then it tells me what I'm at the end. And I said 50, and that's exactly where we are. Okay, so this is a different style again, 1/2-inch drive, and it's a deflection style. And it uses the torquing method or turning method to actually create the torque. This is again the exact same style, except it is a larger capacity. This one is a 3/4 drive, and it also has for high torques, and this one goes up to 600 foot-pounds. So it's going to be pretty hard to pull 600 foot-pounds on this short little bar. So it actually has a bar that goes in, locks in position, and then we have the increased lever point that allows us to get to that torque. I highly recommend that if you are doing a torque from here out to the far end of this, that you have somebody hold this if it's too far from you to be able to pull that torque. So if I was pulling 600 foot-pounds, I'd probably need to use my body more effectively with double hands on it to pull it to that torque. Never choke up on the torque wrench, because if you choke up on it, now the torque goes from here to here, deflecting the scale, when it's actually meant to go from here to the end where the technician is pulling on it. So that changes the torque ratio, and a lot of people tend to do that because they're trying to use their body to torque it. They should be out here kind of doing a rowing effect when they're torquing. So they should be pulling like this or pulling like this. Never push on a torque, because when you push on the torque and the fastener breaks or the socket breaks or the tool comes off, then you fall forward and you could potentially run the risk of hurting yourself or damaging the piece of equipment. Next one here is the very large snap-on torque wrench. This one goes up to 650 foot-pounds, typically used for torquing wheels. It is a dial style, and it's a click stop. So I'm not going to demonstrate this one. I don't have a socket in here for it, but this does the exact same thing as the smaller click stop wrenches. And again, you use the right size wrench for the appropriate job. So when we talk about using the right size wrench, for example, this inch-pound meter, or let's go into the foot-pound torque wrench. So this one goes from 25 to 250 foot-pounds on the scale. So when we look at this scale on here, we want to try and do the torque within the mid-range of that torque wrench. If we are torquing 30 foot-pounds, we don't want to use a 250 foot-pound torque wrench. We want to use one that starts down around 0 or 5 foot-pounds and ends at 50 or ends at 100, because we want to do the 50 foot-pounds. We want to be right in the middle of the range. So it's not a good idea to use this to torque small values, so the minimum scale at 25, or it's not a good wrench to use if we're torquing to 250, because then we're at the high end. We would want to use one that would be 300 or 400 or even 500, or maybe even the large Snapple one at 600 foot-pounds, because if we're torquing at 250, we're kind of right in the middle of that range. And that's where the torque wrenches tend to be most accurate, and that's where they tend to calibrate them. They don't always calibrate them down at the low end. They calculate them and calibrate them in the mid-range. So make sure you pick the appropriate size torque wrench for the job. And most torque wrenches are rated in foot-pounds, inch-pounds, or Newton meters, and manufacturer specifications go by those particular values. So that's the gist of looking at a bunch of different torque wrenches and the procedures that you would use for attaining the correct torque. And again, don't forget your posture, because we want to do everything as safe and as accurately as possible.